Today we'll discuss ISI's 2022 UGB paper, and the first question is, consider a board having 2 rows and n columns. So let us consider this board having 2 rows and n columns. So we have 2 rows, say R1 and R2, and then we have C1, C2 up to Cn columns. Now each of the entries is either 0 or 1. Now the first question is, in how many ways can this be done such that each row sum and each column sum is even? Now each column sum, it can be even only if either both of them they are 0 or both of them they are 1. That means if we choose 0 in R1, then automatically it will be 0 in R2 in the same way. If it is 1 in R1, then it will be automatically 1 in R2. So we just need to find number of ways to fill this row R1. Now along with column, row sum should also be even. Now row sum will be even if we have n zeros and 0 ones, or if we have n minus 2 zeros and 2 ones, or n minus 4 zeros and 4 ones, and so on and so forth. In the first case, we have all zeros and no ones, so it can be done in only one way, so which is nc0. Now here, all these n, we have to fill 2 of them with ones and remaining with zeros. Now which 2? It can be done in nc 2 ways. Now for the next one, we need to choose any 4. So it will be this nc4, and we'll continue. Now this is nothing but a binomial series nc0 plus nc2 plus nc4. That is when all the subscript take even values, and this is nothing but this is 2 to the power of n minus 1. So answer to this first question is the total number of ways in which they can be filled so that each row sum and each column sum is even is 2 to the power of n minus 1. Now in the second part it says, in how many ways can this be done if each row sum and each column sum is odd? Now in the second part, we are given that each row sum and each column sum, it must be odd. Now if we look at column sum, it will be odd when one entry is 0 and the other entry is 1. So if it is 0 in R1, then it will be 1 in R2. And if it is 1 in R1, then it will be 0 in R2. That means again automatically R2 will be filled according to choices given R1. Now we try filling this first row. Then this first row can have 1 1 and then remaining n minus 1 zeros, or it can have 3 ones and n minus 3 zeros, or 5 ones and n minus 5 zeros, and we'll continue. So we have 1 in one place, and this one place it can be chosen in nc1 ways. Now in the same way, 3 ones, so 3 places for these ones, so it can be done in nc3, again nc5. Now this is nc1 plus nc3 plus nc5, which again is 2 to the power of n minus 1. Now so far this case is similar to that of case A, but then here we have a problem if n is an odd number. Because if n is an odd number, and suppose we have k ones in row 1, then we'll have n minus k ones in row 2. Now since sum of number in any row, it must be odd, so this k, it must be an odd number. Now n is odd, k is odd. In this case, this n minus k, it will be an even number. So in this case, sum of numbers in row 2, it can never be odd. So this second case is valid if and only if n is an even number. So if n is an even number, then in that case, the total number of ways it can be done in 2 to the power of n minus 1. So answer to first part is 2 to the power n minus 1, irrespective n is even or odd. And for the second part, answer is 2 to the power n minus 1 if and only if n is an even number. Now here the question is, consider this function fx, which is this summation k varies from 1 to m x minus k to the power 4 for all x belongs to R where m is greater than 1. Now we need to show that fx has a unique minimum and we need to find the point where this minimum is attained. Now if we find f dash x will be this summation k varies from 1 to n, and this is 4 x minus k cube. And if we find f double dash x will be this summation k varies from 1 to m 12 x minus k whole square, that is always greater than 0. Now when second derivative is greater than 0, that means this curve is always opening upwards, and if it is opening upwards, it will have a unique point of local minima. So it will have a unique minimum. Now in this case, we also need to find the point where this minimum is attained. Now if we look at this f dash x is 4, and then it is x minus 1 cube plus x minus 2 cube up to x minus m cube. Now if we take them pairwise, then we can write this as, suppose this summation x minus r whole cube plus x minus m minus 1 plus r. So if r is 1, it will be x minus 1, and here will be x minus m. If r is 2, it will be x minus 2, and here it will be x minus m plus 1, which is the preceding factor. So we can factorize all of them, and there will be this cube, that is a cube plus b cube. We can write this as summation, and this is a plus b. So it will be x minus r plus x minus m minus 1 plus r, and then it will be x minus r square plus x minus m minus 1 plus r whole square, and then minus ab, which is x minus r, x minus m minus 1 plus r. Now here r and r will cancel. So from all the pairs, this factor 2x minus m plus 1 will be common. So we'll get this f dash x as 2x minus m minus 1, and then plus some quadratic polynomial, say gx. Now if we put it equals to 0, we'll get x equals m plus 1 by 2. So this function will have a unique minimum, and the point of that minimum will be x equals m plus 1 by 2. Now here the question is, consider a parabola y square equals 4x. So we have this parabola, which is y square equals 4x, and then we have this straight line, which is y equals x plus 2. Now it says P is a variable point on this line. So we have this point P, and from this we have drawn two tangents, and these point of contacts are Q1 and Q2. Now we need to find locus of midpoint of Q1, Q2. So this is this point Q, and we have to find locus of this point Q. Now suppose this point Q is alpha, beta, and this point P is, suppose, h comma k. Now since Q is midpoint of this chord, we know that we can write equation of this chord as t equals s1. Now t is beta y minus 4 x plus alpha by 2, and it will be equal to beta square minus 4 alpha. So we can write this as beta y minus 2x and it'll be equal to beta square minus 2 alpha, and that's our first equation. Now from this point P, we have drawn two tangents. So for this point P, this is chord of contact, and we know that chord of contact is given by t equals 0. Now if we write t equals 0, this equation will be ky, it is equal to 4x plus h by 2. So we can write this as ky minus 2x and it will be equal to 2h, and that's our second equation. Now both these equations, they represent the same line, and if they represent the same line, then from here we can write beta upon k, it is equal to 1, it is equal to beta square minus 2 alpha upon 2h. So from here we get this condition that beta equals k and h equals beta square minus 2 alpha by 2. Now we need to find relationship between alpha and beta. Now this h and k, it lies on this line. So from here we can write k equals h plus 2. Now k is beta, so it will be this beta, and h is beta square minus 2 alpha upon 2 and then plus 2. So it will be this 2 beta equals beta square minus 2 alpha plus 4, or we can write this as beta square minus 2 beta plus 1, and it will be equal to 2 alpha minus 3. Now this is beta minus 1 whole square, and this is 2 alpha minus 3 by 2. Now we'll change alpha with x and beta with y. So this required locus will be y minus 1 whole square, and this is 2 x minus 3 by 2, and this is the answer to this question. This is a very straightforward concept, and I've already discussed such questions in conic sections. So there's nothing new in this question. Now here the question is, let px be an odd degree polynomial in x with real coefficients. Now show that this equation p of px equals 0 has at least as many distinct real roots as the equation px equals 0. Now suppose this polynomial px, it has k real roots, say alpha 1, alpha 2 and alpha k. So we can write this px as x minus alpha 1, x minus alpha 2, x minus alpha k, and then some function, say fx. Now if we look at p of px, we can write p of px as px minus alpha 1, px minus alpha 2, and then px minus alpha k fx. And if we put it equals to 0, then for any general root, say alpha r, we can write px equals alpha r, where r, it can take the value from 1 to k. Now since this px, it is an polynomial of odd degree, and if it is polynomial of odd degree, px equal to alpha r, it will have at least one solution. Or we can simply take this function px, so we can write p of px will be equal to p of alpha r, and p of alpha r is 0. So corresponding to every root of px, we'll get a root of p of px. So this equation p of px, it will have at least as many distinct real roots as the equation px equals 0. Now here the fifth question is, for any positive integer n, let fin denote the number of divisors of the n of the form 3k plus I. So that means this f1n is number of divisors of n which are of the form 3k plus 1 and f2n is number of divisors of the form 3k plus 2. Now we need to find this f 5 to the power 2022, which is actually f1 5 to the power 2022 minus f2 5 to the power 2022. Now if we take 5, so this 5 is congruent to modulo 3, and 5 square is 2 square 4 and 4 is 1 modulo 3. So this 5 to the power 2k plus 1 will be this 5 to the power 2k, which is 1, and then 5, which will leave the remainder 2. So it will always be congruent to 2 modulo 3, and 5 to the power 2k will be congruent to 1 modulo 3. So if we look at all the divisors of this number, the divisors will be 1, 5, 5 square up to 5 to the power 2022. Now if we look at f1 2022, it will include 1 and then it will include all the even parts of 5, and all the even parts of 5 is 1011. So it will be 1 plus 1011, and which is 1012. Now if we look at f2 5 to the power 2022, now we'll get this remainder 2, or it will be of the form 3k plus 2 if and only if power is an odd power, and it'll be an odd power when it is 5 cube up to 5 to the power 2021, and total number of cases will be again 1011. Now we need to find the value of f5022. So this value will be 1012 minus 1011, which is 1. So answer to this first part is the value of f 5 to the power 2022 is 1. Now for the second part, we need to find f 21 to the power 2022, which we can write f 3 to the power 2022 into 7 to the power 2022, and this is f1 21 to the power 2022 minus f2 21 to the power 2022. Now for both f1 and f2, we cannot include any 3, because if 3 is included, then it will be a multiple of 3. So we'll get this congruent 0, which we do not need for f1 and f2. So for f1, we need 7 to the power n congruent 1 modulo 3, and for f2, we need 7 to the power n congruent to modulo 3. But if we look at 7, then 7 is 1 modulo 3. That means any power of 7 will always be congruent to 1 modulo 3. So in this case, there will be no f2n. So this case is not possible. So for this, value of f2 21 to the power 2022, it will always be 0. So this value, it is 0. Now what about f1 21 to the power 2022? Now I will include all the values from 1, 7, 7 square 2, 7 to the power 2022, and there will be 2023 numbers. So value of this expression will be simply 2023. So answer to the second part is 2023. I had to re-upload the solutions primarily because of this question number 6. While solving it, I have assumed a symmetry in P6 which was not there. Hence, the entire solution went for a toss. So what I'll do is I'll solve it in a more general way. Now suppose we have points Pn Pn minus 2 and Pn minus 3, and they're represented by these position vectors Pn, Pn minus 2 and Pn minus 3. Now since Pn is midpoint of these two, we can write vector Pn will be equal to Pn minus 2 plus Pn minus 3 whole divided by 2. Now if you look at the points Pn and Pn minus 1, then the line segment between them is given by Pn minus Pn minus 1. So what I'll do is, I'll write this as Pn minus vector Pn minus 1, and here will be this minus Pn minus 1, and what I'll do is I'll add Pn minus 2 and I'll subtract Pn minus 2. So it'll be this plus 1 by 2 Pn minus 3 minus Pn minus 2. Now this vector Pn minus 1, it will constitute length of the triangle. So what I'll do is I'll assume this as some vector Ln. So I can write this as vector Ln will be equal to minus, and this is Pn minus 1 minus Pn minus 2. So it'll be this Ln minus 1, and if we take minus common, it'll be Pn minus 2 minus Pn minus 3. So it'll be this Ln minus 2. Now we know that area of triangle formed by Pn minus 1 and Pn minus 2, it will be 1 by 2 into cross product of Ln and Ln minus 1. So what I'll do is I'll take cross product with Ln minus 1. So I can write this as Ln cross Ln minus 1. Now here will be this 0, and then it'll be this 1 by 2 Ln minus 2 cross Ln minus 1. Now we multiply it with 1 by 2, we can write 1 by 2 Ln cross Ln minus 1 will be equal to 1 by 4 Ln minus 1 cross Ln minus 2. Now this is suppose area of nth triangle. So this is An and will be equal to 1 by 2 An minus 1. Now using this iteration, we can write it will be 1 by 2 square An minus 2, 1 by 2 cube An minus 3, and will continue, and it will be this A3 1 upon 2 to the power n minus 3. Now this is area of the given triangle. So if we take this limit n tends to infinite, then 1 upon 2 to the power infinite it will be 0. So this An, it converges to 0 as n tends to infinite. Now for the second part, it says prove that Pn lies on L, where L is line segment joining P1 and P5. Now we know that P9 is midpoint of P7 and P6. So it will be this P7 plus P6 divided by 2. Now P7 is midpoint of P5 and P4. So it will be this P5 plus P4 by 2, and P6 is midpoint of P3 and P4. So it will be this P3 plus P4 divided by 2 whole by 2. So now we can write this as P5 plus P3 plus 2P4 whole divided by 4. Now we know that P4 is midpoint of P1 and P2. So it will be this P1 plus P2 by 2. So we can actually write this as P5 plus P3 plus P2 plus P1 whole divided by 4. And P5 is midpoint of P3 and P2. So we can write P3 plus P2 as 2 times of P5. So this is actually 3 times P5 plus P1 by 4. So basically this P9, it divides P1, P5 in the ratio 1:3, and therefore this point P9, it lies on line joining P1 and P5, and this is what we need to prove in this question. Now the next question is Px is 1 plus 2x plus 7x square plus 13x cube for all x belongs to R. Calculate for all x belongs to R this limit n tends to infinite Px by n to the power n. Now first we'll find form of this limit. Now this is P0 and P0 is 1. So this is 1 to the power infinite form. And we know that for 1 to the power infinite form, we have this direct shortcut. So it will be this e to the power and then this limit n tends to infinite. Now this is f to the power g and shortcut is g. So this is n into fx minus 1. So it will be p x by n minus 1. So it will be this e to the power limit n tends to infinite and this is n. Now p x by n is 1 plus 2 x by n plus 7 x by n square plus 13 x by n whole cube and then minus 1. So this 1 and 1 will cancel and we'll multiply this n inside. So this is n. Here will be simply 7 by n and here will be 13 by n square. Now if we take this limit n tends to infinite, this expression will be 0. It will also be 0. So this limit will be simply e to the power 2x. So that is the value of this limit. Now this question number 8 is very simple and we have already discussed this question in application of derivatives compendium. So there what we have done is we have taken this sin x plus cos x as t. Sin x plus cos x as t. Now we square it, we'll get 1 plus 2 sin x into cos x as t square. So we can write sin x into cos x as t square minus 1 by 2. Now say this expression is, now we can write this as E equals, now this is sin x plus cos x which is t. Now 10x plus cot x is sin square x plus cos square x upon sin x cos x. So it will be 1 upon sin x cos x which is t square minus 1 by 2 and then plus, now secant x plus cosec x will be sin x plus cos x which is t upon t square minus 1 by 2. Now what we'll do is we'll take these together. We can write this as mod of t plus, and this is 2 into 1 plus t, and this is t square minus 1. Now here 1 plus t will get cancelled, so we can write this e as is mod of t plus, now it will be this 2 upon t minus 1. Now we'll find absolute maximum and absolute minimum for this function for t which is sin x plus cos x. That means value of t should lie between minus root 2 and plus root 2, and this t, it should not be 1. Now we differentiate this. We can write this as 1 minus 2 upon t minus 1 whole square equals 0. So it will be this t minus 1 will be plus or minus root 2, or value of t is simply plus minus root 2 plus 1. Now we'll find the value of this expression e at the end points and also at these points and see which value is minimum. So if we put t as root 2, we'll get e as root 2 and this is 2 and this is root 2 minus 1. When we rationalize this, we can write this as root 2 and this is 2 into root 2 plus 1. So it will be this 3 root 2 plus 2. So we'll get this value when the value of t is plus root 2. Now if we take t as minus root 2, we'll get the value of e as minus root 2 and then minus 2 upon root 2 plus 1. So it will be this root 2 and this is 2, and if we again rationalize, it will be this root 2 minus 1 which is 3 root 2 minus 2, and we take t as 1 plus root 2 we'll get this E as 1 plus root 2 and then plus 2, and t minus 1 is simply root 2. So it will be this 1 plus 2 root 2, and if we take t as 1 minus root 2, we'll get this E as 1 minus root 2, and here will be this 2 upon minus root 2. So it will be this 2 root 2 minus 1. Now out of these 4 values, this is the minimum value. So the minimum value of this expression will be 2 root 2 minus 1. And now the final question is, find the smallest positive real number case such that this inequality holds, which is mod of z1 plus z2 plus zn is always greater than or equal to 1 upon k mod of z1 plus mod of z2 plus mod of zn. Now for this, what we'll do is, we'll let, say, any zr is xr plus iota yr, and we have non-negative real and imaginary parts. That means any xr and yr, they are always greater than or equal to 0. Now if we look at mod of z1 plus z2 plus zn, it will be nothing but it will be under root of x1 plus x2 plus xn whole square plus y1 plus y2 plus yn whole square. Now if we consider two numbers x1 x2 plus xn whole square and y1 plus y2 plus yn whole square, and if we take these two numbers as a and b, we know that under root of a plus b by 2 is always greater than or equal to under root a plus under root b by 2. So from here we can clearly say that under root of x1 plus x2 plus xn whole square plus y1 plus y2 plus yn whole square by 2, it is always greater than or equal to x1 plus x2 plus xn plus y1 plus y2 plus yn whole divided by 2. Now we'll cancel this root 2 with 2, so it will be this root 2. Now this expression on the left hand side, it is nothing but it is mod of z1 plus z2 plus zn will always be greater than or equal to 1 upon root 2, and this is x1 plus y1 plus x2 plus y2 up to xn plus yn. Now we can write this as 1 by root 2, and it will be this under root of x1 plus y1 whole square plus under root of x2 plus y2 whole square up to under root of xn plus yn whole square. Now we know that under root of xr plus yr whole square, it will be equal to under root of xr square plus yr square plus 2 xr yr, and will be greater than equal to under root of xr square plus yr square. So it will always be greater than or equal to 1 by root 2 under root of x1 square plus y1 square plus under root of x2 square plus y2 square plus under root of xn square plus yn square. Now this is nothing but this is mod z1, mod z2 and mod zn. So it is 1 by root 2 mod of z1 plus mod of z2 plus mod of zn. So that means the smallest positive value of k in this case will be simply root 2. So the smallest positive value of k is simply under root 2, and that is the answer to this question.